Okay, we're going to look at another related rates problem. So this one has some important differences from the previous ones we've looked at. So one important thing here is that in this problem, we have a quantity that's described, but it's not really a variable. It's a fixed quantity. All right, so in reading the problem here, one of the first things you want to do is organize the information with a picture and a table where you list your variables and the information given about the rates of change. I'm going to start with a picture on this one. So we've got level ground and we've got an observer, draw a little person here. And that person is standing 700 feet on level ground from a launch pad. I'll just put a little X there at the launch pad. All right, so that distance is fixed. If we read the rest of the problem here, it doesn't describe anything about that distance changing. So that is not really a variable, that's a fixed distance. There's a rocket at that launch pad that is shot straight up, and the height of that rocket is going to change. So we're given some information about the height of that rocket changing. So that is a variable. When it starts out, that height of that rocket's on the ground, and then it goes up, and we've got a rate of change for that height. And then we're asked some information about the distance from the observer to the rocket. So we're going to assume we're going to measure that distance from this point on the ground here at the foot of the observer to the rocket. And this is what we're asked to find here, this distance here. I actually probably don't want to use d here because we're going to use some rates of change and talk about d dt, and we'll have d dt, which is too many d's in the problem. So although that is a distance and that's what it's asking, I'm going to use a different letter other than d here, maybe r for distance to the rocket, from the observer to the rocket. Okay, so one important distinction between this problem and other problems is that we have a fixed distance here. So we have some distances that are changing, but we also have a fixed distance here. So when I list my variables and rates of change, I'm not going to include this in that. Okay, so I'm given some information here about a height and a rate of change of a height. The rocket is going up at a speed of 900 feet per second. So we've talked about rate distance and rate and velocity and speed before. So we know that that rate of change, that's a change in distance with respect to time. So that's 900 feet per second. We are asked to find some information about this distance from the observer to the rocket. So this dr dt is what we are supposed to find. And we are interested in finding that out when the rocket is 2,400 feet above the ground. All right, so that is a variable, but we're interested in that at that particular instant. And I may or may not need to know the value of r at that particular instant. Okay, so I need to find an equation that relates these variables. So we make some assumptions here that the rocket's being shot straight up and that we have level ground here, so that what we have here is a right triangle. So they said those things in the problem. So when you look at this right triangle with some sides labeled, the first thing you should think about is Pythagorean theorem. So I'm going to just write that down here. This side is fixed, so we'll have 700 squared plus this side is a variable, so we're going to leave that as a variable. H squared equals our hypotenuse squared. So there's our equation that relates the variables. I might go ahead and square the 700 as I do the problem. Okay, so in doing a related rates problem, you want to organize the information with a picture, label fixed quantities, organize the information about the variables and the rates of change in a table. You want to find an equation that relates your variables. And then from there, you're going to take that equation. I went ahead and squared the 700 here. You're going to take that equation and you're going to differentiate that equation with respect to t. So this is implicit differentiation, differentiating both sides of the equation with respect to t. All right, so the derivative with respect to t of this constant term will just be 0. And so on the left side of the equation, I'll have 2h dh dt equals, on the right side of the equation, 2r dr dt. dr dt is what we're supposed to find. We know dh dt, 900 feet per second. We have a value to plug in for h at a particular instant. I will need to find a value for r here to plug in so that I can find the dr dt that I'm asked to find. So we're going to have to go back over here and do a little bit of work. Sometimes we need to know all of these values to do the problem, and sometimes we don't. Okay, but this time we will. So I need to find that r when h is 2400. So I'm going to use my Pythagorean theorem here to help me find that. So I'll just plug in the 2400 for h. So I'll have 700 squared plus r squared equals 2400. That's not right. I have to put the right letters in the right places. Put the number in for h, and I'm trying to find the number for r. All right, so 700 squared plus h squared, h is the one I know, equals r squared. There we go. Okay, so I'm just going to square these numbers, add them together. When I do that, I'll get 625 with 4 zeros behind it. And then when I square root that, I'll get 2,500. When I square root that, I'll get 2,500 feet. Okay, so again, sometimes we need to know all those values in that chart, and sometimes we don't. I usually wait till I get to this step after the implicit differentiation to decide whether I need to do any extra work over there or not. So at this point, though, remembering dr dt is what we're interested in finding, we're just going to plug in the values that we have for all of these other numbers and then solve for dr dt. Okay, so our h was 2,400. dh dt was 900 feet per second. That's a positive rate of change because our h was increasing. Our r at that particular instant was 2,500. And we're trying to find dr dt. Okay, so we can just divide through by this product, 2 times 2,500. And you can simplify that before you divide through or after. I'm just going to do that after. Okay, so there's a lot of reducing that we can do here. Divide this out. There's some 2's that cancel, some other reducing that we can do. When you do that and simplify that all the way, you should get 864. And I want to make sure that I label my answer using units that make sense in the problem. R is a distance along a side of a triangle, so that would be measured in feet. Our distances in this problem are measured in feet, and time in this problem is measured in seconds. So this would be a rate of change in feet per second. Since that's a positive rate of change, I know that that r value is increasing. Positive rate of change, so r is increasing at this rate.